Hi all! In this video we will derive Poiseuille's law for a cylindrical tube because in most biological systems the vessels that carry blood and whatnot, or water or nutrients or whatever, will be cylindrical. So in either the notes or a previous video you saw a derivation for the velocity profile in a cylindrical tube. So we are going to have cylindrical tube like this that will have a radius big R, and then there's going to be a pressure on this face. It's going to be P1, and there's going to be a pressure that is on this other face that will be P2. And the idea here is we're going to take little cylindrical shells. So we're going to take something like this. It's really thin. And what we're going to do is we're going to use the velocity profile at that distance out r. So there's the center, we go at a distance little r, so we're going to have the velocity profile at that r times time. So this is going to give us velocity times time is just going to give us a distance. And then we're also going to multiply this by 2 pi r dr. So this is sort of just the circumference, and then this is the thickness, so that we end up getting a volume. So this ends up giving us the volume for a cylindrical shell. And what we want to do is we want to add these all up. So the way that you add everything up is you integrate this from 0 to big R, so from no radius up to the large radius. And this will give us the total flow rate Q times delta T, because this is a volume flow rate, so this is volume per time. If you multiply by a time delta T, then you'll just get a volume. So what we can do now is first see that on both sides we're going to have a delta T. We can just cross that out, and then we'll do this integral. So what we need to do is we need to input for the velocity profile in the z direction, where this is the z direction, for different r. So the actual derivation of this v of z of r is something you can look in the notes or in another video. We're just going to use that result right now. So we're going to do from 0 to r of P1 minus P2 all over 4 times the length of the tube times eta. So we're going to have, this tube is has a length L, and it has a viscosity, the fluid flowing in it has a viscosity eta. And then this will be multiplied by big R squared minus little r squared, and then we have the r dr, and we also have a 2 pi just because of this right here. That's going to be equal to our volume flow rate Q. So we can pull out everything that's a constant, so we'll get 2 pi P1 minus P2 all over 4L eta, and then we're going from 0 to r of r squared minus little r squared r dr, and that's equal to Q. And now all we have to do is multiply in this r, so we'll get pi over P1 minus P2 all over 2L eta 0 to r of big R squared r minus r cubed, all of that dr equal to q. And then what we can do is we can come up here and we can continue the integral. So this is now going to be pi over p1 minus p2 all over 2L eta, and then we integrate this. So this is just a constant times r, so you add 1 and divide by the new power, so it's going to be big R squared, little r squared all over 2 minus, add 1 and divide by the new power, little r to the 4th over 4, 0 to big R. So now we just put in our limits. When we put in 0, we're just going to get 0 to the 4th and 0 squared, so we're not going to write that one down because it's just going to be 0. So this is p1 minus p2 over 2L eta, and this is going to be big R to squared times big R to squared because you put in the R here, so you get a 2, and then this is big R to the 4th all over 4. That's going to be equal to q. And then what we can see, this is big R squared times big R squared. So we can just rewrite this as big R to the 4th. And then we can do 2 over 4 because that's still 1/2. And then what we end up getting so this is going to be just 2 minus 1, so we get pi p1 minus p2 all over 2L eta r to the 4th over 4 equal to q. And then what we can do is we can rewrite this and do a little bit of talking. So 4 times 2 is 8. So what we can do is we can do pi r to the 4th all over 8L eta p1 minus p2. That's going to be equal to q. So this is Poiseuille's law, that the pressure difference across a segment of pipe is going to be equal to, so this is pressure difference, this is volume flow rate, so really what Poiseuille's law is it's saying the conductance, which is right here, so the conductance is a measure of how hard or easy it is to flow through a pipe, that it's drastically dependent on the radius. So some people say exponentially, this isn't exponential, this is to the 4th, but still, this is going as the radius to the 4th, which is, you know, larger, is even more drastic than a volume. So volume goes as r cubed, this is going as r to the 4th. So what we see is if you change the radius just a little bit, you're going to have a large effect. So the difference between 1 to the 4th and 2 to the 4th is 15. So 1 to the 4th is still 1, 2 to the 4th is 16, which is quite large. And we'll also notice that the conductance is just related to geometrical factors, so the radius of the pipe, the length of the pipe, and then also fluid parameters, so the viscosity of the pipe. So the conductance times the pressure is going to equal to the volume flow rate, and for Poiseuille's law, it's going to be drastically dependent on the cross-section, so the radius, and it's weakly dependent on the length. All right, thank you.